Greetings and welcome back. So, now what we're doing is an introduction to what I'm going to refer to as the forces of evolution. This is a primer for population genetics, which we'll do later, actually mathematicizing these cartoons. So, in the previous vignettes, I talked about the various ingredients, the factual ingredients behind the evolutionary process, the existence of freestanding variation, the fact that that variation is heritable, and then I argue that there are a variety of forces of evolution, although we focused on selection. The idea being of this notion of an invisible hand that parses the population and decides, with quotes, on which variation is favorable and thereby actually makes it through this evolutionary sieve. So, what I want to do in the next 10, 15 minutes is just try to give an introduction to this, I think, this very nice and provocative graph. And there's much to be learned from this. I think it's most useful and most interesting when one comes at it from a mathematical point of view. But as a quantitative introduction, what I want to do here is I want to start out with what I'll call our evolutionary null model, which is Hardy-Weinberg equilibrium. And the idea here that's very interesting is you have some ancestral population, and the way that that's depicted is through different colors. The different alleles correspond to different colors. And then the mating process, I want you to think of as basically what was once referred to as beanbag genetics. I have an urn. The urn is full of a bunch of marbles. The marbles are colored. We're going to think about the case where the marbles are either red or white, or red or black, or something, and they're at a certain proportion. And we reach in with our eyes closed, and we have a given generation n, and we're going to find the n plus 1th generation by choosing pairs out of the with replacement. In other words, I reach in, I pull out one, I look at it, and I say, red is going into the descendant generation. Then I put it back, and I stir, and I pull another one out. And I do this over and over. And the question that was addressed by Hardy and Weinberg is a deep and very interesting question. And that was, what will happen to the allele frequencies over time? In other words, if I do this process where mating is just random, I think of the population as being a bunch of every single member of the population in the two allele and one gene type model is there's some frequency of red and black or red and white balls, and the population has a certain size n, and so that means if we're thinking about diploid organisms, then that means there will be 2n marbles. And to find the next generation, as I said, we go through this process of pulling out marbles. So what's really cool, and I will do the mathematics later, is that we can compute the probability of getting the red homozygote, the black homozygote, or the heterozygote, which is red black. And as I said, this is the beanbag genetics 101. We start out with the parents. There's a certain number of 1 and 2 alleles. We make a pool, which I think of as being an urn, and then the offspring are gotten by drawing and basically keeping the population size fixed. And what comes out of this is, first of all, this plot is showing me, if the frequency of p, let's call p the probability or the frequency of the red marbles, then the probability of pulling twice a red is p squared. The probability of pulling twice a black is q squared, and the probability of pulling a red and then a black or black and then a red is 2pq. And the thing that we'll be able to show mathematically is that the allele frequencies are invariant over this process of random selection, as long as the population is sufficiently large. And that brings me to my next point, which is genetic drift. So here, if I have a finite population, if we were in the classroom right now, I would illustrate this by basically asking everybody whether they were born on an even or an odd day. And what you'd see is out of 10 people, I would generally not get 5 and 5. I would get 6 and 4, or 7 and 3, sometimes 5 and 5. Sometimes I get something bizarre like 8 and 2. And the point is if I have a small population and I'm doing nothing more than just coin flips, over time what will happen is that population, the frequencies of red and black will change over time. That's evolution. And so let me give you an introduction to that through experimental evolution, I think, in a really cool way. So many people in the class had mentioned an interest in synthetic biology, and I wanted to note that there was already in the late 1800s a synthetic biology experimental evolution experiment by this guy Dallinger, where what he did is over time he increased the temperature of the culture. So he started out with an incubator initially at 60 degrees Fahrenheit, and by the end of the experiment, which was I think over 7 years, the temperature was 158 degrees Fahrenheit, and now the organisms, they're no longer capable of living at the original 60 degrees. They've definitely and definitively undergone evolution. So in this spirit, I want to tell you about this beautiful experiment that I'm a huge fan of by Bury, in which he considered the evolution of eye color in a case where the allele was neutral. And when I say neutral, what I mean is that there was no benefit one way or the other to having red or white eyes. And so the concept of the experiment, note that it's a single author paper, so he did all this himself, is he had vials, 107 vials, and shown on the left. And each vial had initially 8 males and 8 females. All of them were heterozygous. That means that each harbored one red and one light white allele. And what he would do is he would collect eggs, and then he would basically hatch the larvae and then collect randomly 8 males and 8 females from the next generation. And you see that over on the right-hand side. And what I want you to note is that although there are still a lot of oranges left, there's now a couple of whites and there are a couple of reds. What does that mean? It means that those offspring, by random chance, got either 2 white or 2 red alleles. That's very deep and very interesting. So he repeated this. As I told you, there's 107 vials. He repeated this over roughly 20 generations. And the thing I want you to notice is that as you sweep across, and we get to the right-hand side, what we see is that the vials are either strictly white or strictly red. What does that mean? What's the interpretation of that? It means that the population has evolved from orange-eyed heterozygotes to red or white-eyed homozygotes. And that short of having some mutation, the population is now stuck either being purely red or purely white. There's no way to go backwards. And this is a beautiful rendering of the experiment, and we will calculate this later using the so-called Wright-Fisher model, which really amounts to using the binomial distribution. What you see here is on this axis, we're looking at generation number, and then on this axis, the x-axis, what I would say we're looking at is the frequency of, for example, the red allele. And what you see is the initial population, there's a big spike. You see where this says 107. That means all the flies were at 50%. 50% red allele, 50% white allele. Then what happened over time, you can see this thing originally was a Gaussian. This is basically a diffusion process, if you like. It's diffusion in a finite box. And then over time, when the allele frequency collides either with 0 or 1, it's fixed. The language is that it's fixed in the population. Because once it reaches that barrier, it's stuck. These are absorbing boundary conditions, is one way to think about it. So it's a really, really cool and interesting experiment, and we will talk that through later when we think about population genetics. And then I wanted to just say a quick word about mutation. So here, I want you to imagine, again, it's a 2 allele model. I want you to imagine that A1 can be converted into A2 with a rate constant mu. A2 can be converted into A1 with a rate constant nu. And we can work out the dynamics of this system given any initial condition. You can start with an initial distribution of A1 and A2s. No matter what it is, over time, this thing will evolve, and in the long time limit, it will reach a steady state. And that steady state is related to the ratio of nu and mu. So, this kind of model has a steady state distribution. So, what happens here, you can see, and again, we will calculate this later, the probability of having a given allele, we start off maybe in some unnatural way, and in the long time, over many generations, it saturates to the equilibrium value. And the way I want you to think of that is that the conversion of A1 to A2 is balanced by the conversion of A2 to A1. That's what it means to be in steady state. So the last of the forces of evolution that we'll consider here is natural selection. We already talked about this in the previous vignette, but I wanted to just come back to the finches. So let's remind ourselves of the experiments of Peter and Rosemary Grant in the Galapagos. And so what you see here is a very interesting histogram where what they could do is they not only measured the beak sizes, but they also knew what the birds ate. And so you can see the diet categories at the bottom: small seeds, small and medium seeds, or seeds of all sizes. And depending upon the beak depth, which is the y-axis on the histogram, the birds either favor one kind of seed or another. And the thing that I think is really quite amazing is that you can measure the breaking force for seeds. And I already mentioned this, I think, in an earlier vignette. I mean, I always marvel at the fact that a really modest change, a 0.5 millimeter or 1 millimeter change in beak depth, is sufficient to change the propensity for which seed will be used by a given bird. And in fact, there was this comment that I show you here. Finches with big beaks, 11 millimeters deep, could crack open the caltrop seeds in 10 seconds. Finches with beaks 10.5 millimeters deep needed 15 seconds. If a bird's beak was 8 millimeters deep or less, it took so long to crack caltrop seeds that the bird gave up on it altogether. And the two pictures on the right are mainly meant to illustrate that, as we have in California, from one year to the next, it can be a really different story in terms of the plants and the level of seeds that are available. So the thing that they found is that in, I think it was 1977, there was, I don't remember if it was an El Nino year or what, but what you can see is that in 76 there were 751 birds. In 1978 there were 90 birds. And the little blue arrow at the bottom of these two diagrams show you the mean beak depth. And so the claim is that there's actually a change in the beak depth, which is real-time evolution as a result of environmental forces. One of the questions that we'll ask in this course, and hopefully, if the pandemic permits us, we'll go to Occidental College to their bird collection, and we'll actually measure beak depths. And the reason that Victoria and I think this is a very useful exercise is we want to know whether or not you will be able to support the size of the error bars that are claimed by the grants. And at the end of the day, I think the conclusion will be you will imagine that with practice and doing this hundreds of times, that you could reproducibly measure the beak depth with quite high accuracy. So the summary of this part was just to say, this is by way of introduction. We talked about the three facts of evolution: variation, heritability, and then selection as the primary force. But I really wanted to at least put you to thinking about whether or not selection is the only null model that you want to have in mind for a given thing that you see in the living world. In other words, you could make a story about baldness. I noticed some people are bald, and you might have some sort of a selective story or not have a selective story, but maybe you'd come up with one. I don't know. I'm kidding around with that one, but maybe there's some. Let me give you a more serious example, which is you might have a hypothesis about Nepalese people and their hemoglobin, because they tend to live at very high altitudes, and so you might imagine that they have some mutations that allow them to grab onto oxygen better. And that's a fine null hypothesis. But even if we found that it was true, we would have to refute first the null hypothesis of drift, or so those kinds of things. So that's what I have to say about the ingredients of evolution, so to speak.